Hello, AP Calculus students. This is Mr. McKellen, and this is day one of our AP Calculus review. This video is going to be how we work through a problem as in the year 2000, number 3. It was a free response question where the students were given a graph of f prime of x. And the AP can ask a variety of questions about a graph like this. And as we see in part A and B, they ask the most basic questions about attaining relative maxes and mins. So one of the things we want to do is we want to understand exactly what to look for when we're solving a question like this. First of all, understand the graph that they gave you. They gave us a graph of f prime of x. Second of all, understand the information in the writing. An AP question, they'll never ever give you extra information that will not be used in the problem. So if there's information that you find that didn't need to be used, then I would strongly consider looking through the problem and seeing where that information can be used, because you may have forgotten something or overlooked something. So let's get started. They've given me the graph of f prime of x. So in the first part of the question it says, or actually in the statement it says, a figure above shows a graph of f prime, the derivative of the function f. Over an interval from -7 to 7, the graph f prime has horizontal tangent lines at x equals -3, 2, and 5. So what we can do is we can just like mark that as such. We have horizontal tangency there. And a vertical tangent line at x equals 3. So I would suggest drawing vertical tangency there, just to remind you that that's vertical tangency. For part A, find all the values for which f attains a relative minimum. For part B, find all values for where f attains a relative maximum. Justify your answer in both cases. I'm going to pause the video, and I'd like you to consider it, and then after you come up with your explanation, I'll go over my explanation with you. Okay, I'm back. And in order to find where you have a relative min, you're looking for, and I'll write down the explanation first, relative min values occur where f prime of x changes from negative to positive. This happens at x equals -1. That would be a relative minimum location. Relative max values occur at where f prime of x changes from positive to negative. This happens at x equals, it's positive on this side, negative on this side. This happens at x equals -5. I'll zoom out so we can see the whole problem. The next part of the problem says find all the values of x for which the second derivative is negative. This question could also be phrased, find all the values of x for which f is concave down. These are the same types of questions. And how do we use our first derivative to show us when the second derivative is negative? So for part C, whenever f prime is decreasing, f prime prime must be negative. And in parentheses, I'm going to put, just so you know, f must be concave down, because this is a question that they could also ask on the AP test. Instead of asking you about the second derivative, they could ask you, what is the function doing? So when f prime is decreasing, f prime prime must be negative, and now you would just state your intervals. So my derivative function is decreasing on the interval from -7 up through 3. Now right here, this happens when on the interval closed from -7 up to -3. And it doesn't have to be closed. I don't think they take off points for closed or open intervals when you're describing intervals anymore. So, and in fact, it should be open if you want to do it properly, because it really isn't at this point here for the -3, the function is neither dropping or increasing. So the derivative that is, so you have to leave it open. But the AP will not take off a point for that, at least in the last few years they haven't, and they've stated such. So the next interval is going to be from 2 to 5. Most people want to describe the interval from 2 to 5. So a lot of people make the mistake and say from 2, 5, but at x equals 3, the second derivative does not exist. So it's neither negative or positive. It just doesn't exist because of vertical tangency at that point. So what you have to do is you have to describe it as 2 separate intervals. So from 2 to 3 and from 3 to 5. And that's because the second derivative at 3 does not exist. So the last part, they ask us, at what values on the interval do you attain a maximum? There are several ways to describe this. I'm going to go over the method that talks about using signed areas. So I'm going to zoom out a little bit so we can see the picture. And so they want to know when you attain an absolute max. So in order to do this, you have to describe what the function is doing, and you have to describe the points where you could have a possible max. Possible maximum values, we'll also call them absolute maxes, occur at endpoints and critical points. So it's important for the AP that you tell them that you know where your possible maxes are, because you know from the closed interval method that you have to check your endpoints and you have to check critical points. And critical points are where the derivative equals 0 or does not exist. Now, as you look at the function for the derivative, we don't have any non-existent derivatives, but we do have places where you have the derivative is equal to 0. So I'm going to make up a list. I'm going to say we should check out at x equals -5. We should check x equals -1, and we should check x equals 5, because those are critical points within the interval. And we should also check out our endpoints at x equals -7 and at x equals 7. Now, we can exclude x equals -1 from a possible max and x equals 5 from possible max, because at x equals -1, that's a relative min, because the derivative changes from negative to positive. At x equals 5, it's nothing, because the derivative changes from positive to positive, so it just is like a stationary point where the function just it reaches a stopping point, but then it continues to go up from there. So then we consider these 3 points, and we tell a story based on relative comparison of trapped areas under the derivative function, because this is the derivative. So if we imagine that the area, or if we know that the area under the f prime curve is the net change in the function value, and this goes back to the net change theorem, we can assign signed areas. So let's say that I think that this area here is equal to about 2. This area here would be equal to about -3. This area up here, we could assign that to be equal to, if we go with scale, approximately, let's say, 4. And this area here, we would say is another 2. So as we go from, because the net change of the function, as we go through and we consider, imagine that our function value at x equals -7, I'm going to just draw like an axis and try to track our function value. We can explain with comparative areas. Let's say that at -7 we started at a 0 value. We can pick any arbitrary value for where the function starts, but let's say it's at 0, so we have -7 comma 0, and we're going to draw the graph of f of x. In this region here, the derivative is positive, so the function is increasing. Then we hit a 0, and now the function stabilizes at -5, and it starts heading down for 3 units. So here it went up 2. Here it's going to go down 3 up until the 3 point. I'm sorry, until -1. So let me just change that. I'm just doing a rough sketch to show how the function is going up and down based on the derivative, and relatively speaking, by how much. So now it's at a value of -1. Now it's going to go up 4. So to get up to a value of 3 by the time we got to 5. And then it stabilizes, and then it goes up some more. So clearly, by using comparative areas up to 7, clearly at x equals 7, we have our max. And if you can articulate this in your explanation, that you use signed areas, and you show the picture, and that you identify the critical point at -5 to check, you check your endpoints and your critical points. Using this method of signed areas, they should give you full credit on this part. So I hope this video helps you understand some of the basics with using or interpreting an f prime graph or a derivative graph, and I look forward to hearing your comments.